So it's my pleasure to announce the next talk, which will be given by Adrian Ionescu. And he's from the EPFL in Switzerland. And he will talk about, let me read the title. He will talk about Memristive technologies for a future neuromorphic edge. Please, Adrian.
Thank you, Rainer. Thank you. It's really a pleasure being here, and I will start by saying that we also here in these days to also somehow celebrate the career of Professor Wasser. And I want to say here all the appreciation that the community of microelectronics, and I am part of this community, we have for all the things that you have done through your career, all the advancement that you have done in the field of different type of memories, materials, and contribution to the field, and all in good mood and in good relation to all the colleagues. We really appreciate that, and I will try to talk here for the audience, but also for you for this celebration. Thank you, Rainer, very much. And again, the talk would be about Memristive technology for a future neuromorphic edge. I am a technologist, an electrical engineer, and I'm still in the learning period with neuromorphic. So in the last 4 or 5 years, I have a number of PhDs starting in the group working on that. Our main activity were on energy efficient devices. So we are looking at new functionality beyond the CMOS digital era by acknowledging, however, that CMOS is there and is the mainstream technology. And in this talk, I'm going to address very precisely a few topics, like this concept of enabling tiny brain for the edge, which means finally putting more intelligence into the edge, based on what we call today Memristive devices. And here I'm going to give you 2 example classes of these devices for electric FET synapses and maybe also tunnel FET synapses in the future, and vanadium oxide spiking neuron that are also serving spiking sensing type of function. So I will start with this picture of the sky. You know, in the last weeks, we experienced all this solar storm and aurora borealis that have been visible even from Switzerland. And when looking at the sky and the Milky Way, you may ask, well, you feel so small compared to the more than 200 billion stars that are there in the Milky Way, according to estimation between 200 and 400 billion Milky stars. And then you may say, well, humankind, have we achieved any artificial object of this order of magnitude? And then, beginning of the year, if you remember, we had, and this was also in the example of Infineon today, some of the first chips that are reaching this level, more than 200 billion transistor per chip in the NVIDIA Blackwell, with, according to NVIDIA, 576 GPUs with a chip-to-chip link of 10 terabit per second. So transistor is the most abundant artificial object created by humankind, which enabled practically the digital era with which we are confronted. And as you know, everything started with the Moore's law, which in fact is more like empirical prediction that the number of transistors per area will double every 18 months or 2 years, and this continues exponentially. And more than 60-year generation of engineers were able to bring this technology at this level of integration, right? To have more than 100 million devices per millimeter square, all working without any error for 10 years, guaranteed, and at the scale that approaches the atomic scale. And I remember Professor Hiroshi Iwai from Tokyo Tech was saying, it would be difficult to call anything else in the future pico technology, because pico technology would mean that we are practically below the atomic scale. So it seems that there is some room there from 10 nanometer to 2 nanometer to reach the ultimate scaling, and then we have to imagine, as it was mentioned by other speakers, what other type of functionality and what other type of roadblock this technology has because of this high-speed development focus on performance. And of course, as you know, in the history of the world, there is a rise and there is a fall, like it was in the Roman Empire. And we may look, what are the roadblock and the problem that this advanced technology is experiencing? And some of them are related with what we call any technology is a victim of its success. So this technology developed a high performance experience problem in energy efficient, but also in the fact that we have to treat more and more data. So data proliferation, I see it as a problem. So it was mentioned, for instance, that what we'll be calling my talk big brain or data center, worrying us. You have seen also in the Infineon presentation, we are somewhere between 2 and 7% of the electricity of the Earth in data center. And for instance, there are countries in which this percentage is much higher, like in Ireland, is 40% and projected to be up to 27% by 2029. And again, half of the energy in data center is wasted, right, in thermal dissipation. And now with the generative AI, there is even more demand in developing data center with even more energy consumption. Second thing, we all know that there is edge AI vision in which Internet of Things node are going to proliferate, and we have everything monitored by Internet of Things node. Our infrastructure, the buildings, the bridges, the transportation are monitored. People want to monitor also, for instance, climate change by deploying such node. So there is an industrial IIoT domain. There are applications in the medical domain. So there is a projection that in the coming year, even before 2050, will generate 1,000 more data at the edge with Internet of Things node that can reach level of the order of 1 trillion. So this is predicted by ARM. Now the question is, when you look at the infrastructure for this, we are probably not ready for it. And communicating all this data from edge to the cloud is a problem. So there are different solutions that people have in mind, but I believe that overall we have to address practically both of these because otherwise this is not sustainable. And the question is what we can do. Of course, we have on one hand the von Neumann computing and beyond using digital information processing. And my colleague from IBM before, Abu said, oh, if you can do anything in digital, do it in digital, because then you have a lot of advantages. So still, this will continue to exist in part. But then there are this statement that we cannot continue on an ever-increasing processing power, and the future of processing will be based on understanding and drawing inferences from the massive collection of data. And then you have two opposite directions. And this opposite direction are on the left, what I call bio-inspired, and what this conference is about. So doing things inspired by nature, not necessarily mimicking and trying to make a brain, but being inspired by what nature achieved in millions of years in evolution, and maybe even do it better with the technology. And on the other hand, you have this future big brain sitting in let's say, in the cloud, and doing massive parallel computation based on quantum computing. And this is a technology that probably has a longer time horizon. There is a lot of promise and a lot of fundamental concept emerging. So if you look in the recent publication just this week, some people came in with the idea that one of the fundamental properties used in qubit process, which is entanglement, can explain the notion of time. And time as notion in fundamental physics in theory can be derived from quantum entanglement, which is very fundamental change even in the general relativistic theory. So now make it simple as a summary, we are confronted with this stretch out in the cloud will probably have, together with CMOS Big Data Center Quantum, big brains. And the most part of the community, I think, agrees that the edge is the opportunity in building this tiny brain based on neuromorphic technology for autonomous real-time system, right? So now, if you look at other type of limitation of CMOS that we may want to address, as you know, we have the power leakage, but on the other hand, when you make system out of CMOS, you are confronted also with what is called dark silicon, right? And this is an example of a chip on the edge for a mobile phone in which so dark silicon is practically the inability of an advanced, very dense CMOS technology to use all the transistors for computation a single moment of time because of limitation in dissipation. So the smaller the technology node, the larger the fraction of the dark silicon. It can be for 10 nanometer up to 80%. So people try to solve this, to distribute computation. Multi-core was a solution in the past. But one of the things that we may try to do in the future in neuromorphic is to make chips that are less darker, in which, because of the energy efficiency of the neuromorphic, we'll be able to use a larger part of our hardware at the same moment of time. And you may ask as well, what about the brain? And there are many myths about the brain, but in the same time, it's known that the brain is not a full dark system, it's at least a gray system in which not all the neurons are fully used at the moment in time. So maybe you have seen this movie, right? Lucy, in which Lucy is increasing the capacity of using more than the famous myth of 10% of the brain up to 100%. And this is something that at this moment we cannot understand or do, but I believe neuromorphic can address this in a different way than digital CMOS in the future. Now, the neuromorphic edge has the advantage that at this moment has very, let's say, clear specification in which the primary target is inference, is not necessarily dominated by the training. And it's about autonomous system with many applications in which we want to move this decision-making on the edge. And I highlighted here two main attributes, real-time and energy efficiency, that are motivating the communities to work into that. And here, adaptability and bioinspiration can bring a lot of advantages. And I want here just to cite an approach that I have with 3 other colleagues in Europe now, with Elisabetta Kika, that is here in the room, with Denis Flandre and with Gerhard Fedweiss, in which we plan to build in the next year a first demonstrator that will be an end-to-end, all-spiking IoT node, in which practically we'd like to have a first layer of neuron that is sensitive to external stimuli, and then to have all the processing without any analog to digital conversion. So everything in the time domain, the spike domain, in order to reach an advantage in terms of energy efficiency for particular application. This will not replace everything. So now today I want to show you a few examples of technology that can enable that. And as it was some discussion, but I think today people agree what is a Memristive device. I mean, we in general accept that is a device that can retain a state of internal resistance based on a history of applied voltage and current. And there are many candidates today. That is very nice because in general, these candidates have different merits, and they each benchmark one against the other. Again, it was mentioned before that finally, like achieving like in-memory computing here, achieving Memristive synapses, a neuron with any of these technologies of interest, and then the benchmark will depend on what you want to achieve in your application and particular figures that are required by your application. But resistive memory, phase change, ion intercalation technologies, ferroelectrics, all these are standing up and they are under exploration and in more or less different advanced stage. In many cases, we are able to make circuit with it, right? It's not at the level of just a proof of concept of the device. We can make an array of circuit and demonstrate functionalities with interconnected neuron and synapses. So I will give 2 examples of things we are working on. So first will be about how to build ferroelectric synapse based on gating of 2D materials. So Michael Oyken asked a question this morning, if in the future there is any role of 2D material. And we know that many companies are now exploring the potential of including this wafer level in maybe back end of the line or transferring it. And I think there is an interesting potential to make additional function when the scaling is not everything, but the functionality is different in the back end of the line. And this is the idea. Can we build synapses and a neuron in the back end of the line or integrate 3D on CMOS based on this new material? So finally, the synapse function we try to understand it is very simple. You should achieve a kind of programmable conductivity when you transfer and you control the transfer of this information. So my edge device one that I would like to show to you, it's an extremely simple one. It is practically ferroelectric FET made of MOS2 as a 2D material that has high K, doped high K ferroelectric as a backgate. And the function we want to achieve is Memristive non-volatile, in which we have to demonstrate a synapse plasticity. We would like to have spike programmable potentiation and depression curve and demonstrate an exponential STDP curve, right? If you demonstrate all this, you have some benchmark for using this type of device for in an architecture as an artificial synapse. And yeah, there were 3 people working in my group on that. So the first thing we had to do was to develop a very clean, effective stack where we have a certain quality of the ferroelectricity with low leakage. So we were using practically silicon doped half NUM oxide. Sorry for the typo there, half NUM oxide. So we can get a remnant polarization between 15 and 20 microcoulomb per centimeter square with a relatively small quericity field, which will let us to operate this device at few volt and potentially scalable below 2 volt. And as you see here, we have developed practically this gate stack on which we transfer MOS2 from monolayer up to few layer. This is the device with few layer, and we have here gold titanium contact on top of it. And we tested it as first as a memory device, but then we tried to do something that was relatively reported recently in the literature in 2018, how to program practically the threshold voltage of such a device with a pulse scheme in order to achieve potentiation and depression curve that you see here on the right by what is called analog cumulative switching of ferroelectric domain. And this is absolutely possible. It's amazingly nice and easy to achieve it. So you see here different pulse scheme that we have used in which you have to very carefully tune the parameter. It depends a lot of the characteristic of your ferroelectric, of the type of ferroelectric that you have, of the dipole response, and the domain and the size of this domain. But here, as you see, practically with pulse scheme that are varying from 3 to 5 volt, and with pulses that are going from tens of nanosecond to microsecond, we achieve with the pulse scheme number 2 a full potentiation and depression curve with an amazing factor. I think this is among the best ever reported in the literature, 10 to 5 practically in the PSC current. And this, that I can tell you without showing the curve, we have a memory window of around 2.5 volt, and we believe this device has an extremely interesting potential for the future. So we have also demonstrated a full exponential. You can nicely fit and extract parameter of the spike time dependent plasticity curve. And now currently we are calibrating simulation in order to compare this technology in order with other technologies to see the potential of it. And then we said, can we do even better? Because in this domain, we are working in the past a lot on steep slope transistors, which are based on quantum mechanical tunneling FET. And here I'm going to show you that we can make a quantum mechanical synapse that can have this hysteretic with much more abrupt steep transition by using ferroelectric gating of tunneling FETs. And this is something I think very interesting if we want to make synapses in the domain of extremely low current and voltages. So here, what we have imagined is practically now a van der Waals tunnel FET. The advantage of a van der Waals tunnel FET 2D to D that here it's just schematically represented is that you do not have much trap-assisted tunneling at the interface, which usually is killing the tunneling FET property. So if you do a good transfer and you build the right alignment of band, you can achieve a very nice tunneling and abrupt characteristic. And we practically gate it with the ferroelectric, now the 2D to 2D tunneling device. It was a bit more complicated in the fabrication because now we have to use on the same stack practical tungsten diselenide, tin diselenide type of heterostructure that for us has the best alignment to obtain band-to-band tunneling. So this again was very carefully checked, was nicely transferred, and I want to give you just an idea when you do this ferroelectric gating of such a tunnel FET, you may get even something like a negative capacitance effect. So you see the red characteristic is the characteristic with ferro gating in one sweep of the curve. So practically you are boosting the performance of tunneling FET with this type of gate stack. And very surprisingly nicely, you can demonstrate that you can achieve with this quantum mechanical ferro gate tunnel FET the very nice type of potentiation depression, and practically also you can program the conductivity in STDP of your synapse. So we are working on it. What would be the advantage beyond having this a smaller voltage, smaller current? This device is much more stable in temperature as well, right? We know the band-to-band tunneling has very little dependence on temperature. So if you are interested, I can share this with you, the process of doing this double stacking by transfer of tungsten diselenide from sapphire substrate. So this is in the PhD thesis of Sadegh Kamae at EPFL, it's public thesis. So this is the type of Memristive device that we achieve with, we call it negative capacitance tunnel FET. Is not fully matched to letter hysteresis, and we obtain practically a steeper slope. I think this is the smallest slope obtained in such device, and we multiply by a factor of 1,000, what is called the ICNCE current, which is the region of current where the slope is smaller than the subthermiomic limit of 60 millivolt per decade. And we have an overdrive that is significant. And here important is maybe good for the PhD that, of course, you may have one experiment of this kind that looks very interesting, but we always ask our student to repeat it and to show, is this repeatable? And repeatable as performance, as behavior. So we try to do this on multiple devices and see variability, because otherwise you'll never convince industry. So here there are 3 of these devices that were mentioned, this effect has been demonstrated. So now just to finish on that, we believe that this is a very interesting future. Maybe I answer myself in another way the question of Michael. Yes, in the future we may imagine a platform in which 2D material, 2D FET, 2D Phi FET, 2D 2D tunnel FET, all this type of, 2D ferroelectric tunnel FET, you can have also this one, can be integrated in kind of a platform where steep slope devices operating at low voltage together with neuromorphic are building blocks for building energy efficient application. Now, what about the neuron? When you are looking at the neuron from some, if you want, I can simplify a lot, but it can be seen as a oscillator in which you control certain characteristic of this oscillator, like a voltage control oscillator, for instance, that is spiking, is generating train of spike. And of course, if you say such a thing, immediately you can build an artificial neuron in CMOS technology, like my colleague Giacomo Indiveri built it 2006, right? Quite a number of years. But then you will need a number of transistors and you will need capacitor. And what is very interesting as figure of merit is, of course, scaling, but in the same time, the energy efficiency you are getting. One metric is energy per generated spike, right? And here, to be competitive, however, with what nature is doing, you should achieve levels that are sub-picojoule per spike. There were different types of neuron technology proposed. As this technology was scaling down, then people proposed and reduced this power of energy per spike. But what is very interesting is here, when you see the role of emerging technology, phase change, magnetic tunnel junction, MOT insulator like vanadium oxide, ferroelectric material, all this can be used now to have a particular device that has a memristive behavior to build, maybe even with 2-3 transistors around, an oscillator that behaves as a neuron and is tunable, and it can reproduce the characteristic that we need for computation. So I will show you one example in which, by using reversible metal insulator transistor material, it can be exploited in order to build such neuron. So there is a long debate here in vanadium oxide about the mechanism that stays and explain this transition between the insulating state and the metal state that happens around 68 degrees C. And it seems today that only a theory that combines phase change plus the theory of a highly correlated material in which electron-to-electron interaction is not neglected can explain this transition. Again, you don't have the full model, but people try still to debate and understand this. Sometimes we can go faster than the theory in the experiment, and here, essentially what we like to exploit is what you have here on the right, left-hand side, the band gap collapse that here happens at a certain temperature with a contrast and resistivity of 3 orders of magnitude. And temperature is one stimuli, but there can be other type of triggering of this effect. And one of the most interesting is that you can electrically induce this. And people show that electrically induced reversible metal insulator transition can happen practically by an explanation of creation of filament of conduction. And if you design the film properly with a certain dimension, at a certain thickness, you can achieve, like in my plot here, hysteretic curve in a memristive behavior that here is non-volatile below 1 volt. So this is what we want to use, and to say now, if we make memristive type of device based on this, it will be extremely sensitive to your environment. Now, there are many materials you can use for that. So among these, you see here a multitude of metal oxide and oxide of different alloys of different metals. The interesting parameter you have to look at is the transition temperature, the horizontal axis. So this should be higher than the room temperature, 300 Kelvin. And then you need a high contrast. So this vertical dimension of the bar should be as large as possible. For a good switch, you need 2-3 orders of magnitude. And you see, vanadium oxide stands here as a very, very interesting candidate. It's also interesting because it's not a rare element. You find it in many minerals, and it's not toxic. It's even in the water of the ocean. So in principle, has not much used for the electronic industry till now, was used as an alloy of steel. And in other applications, in pottery, there are applications that are related to his negative refractive index in the optical domain. But in electronics, it was relatively recent. And what we have done here is something, again, extremely simple. So in reality, we try to have such a resistive switch that switches electrically between a resistive state that is very high. Here, this is the current, and this is the voltage on this VO2. So then you can switch it up with a voltage of 1 volt, and then it switches down within 0 and 1 volt. And then we practically bias it with a MOS transistor that is in saturation. So we choose the bias so that this is in saturation. Now the voltage on this transistor is the supply voltage minus the voltage on the VO2. So you have to put the saturation curve oppositely. But you see, now operation point, very simple electronic basic exercise to find the operation point of this is the intersection of this curve, and then you have two unstable points. So this is an unstable oscillator that, if you fine-tune it with a capacitor at the output, will generate a train of spikes. So the nice thing is that you can generate this train of spike and shape it according to the parameter of your material, the R on, R off, the level of MIT and IMT transition. So you can design the spike as you wish, or you can tune it with the voltage that you apply on your system. And with this, what we have done after making such oscillator, we have looked particularly at the sensitivity of the vanadium oxide to low energy photon. And what does it mean? It means that you are exposed this to electromagnetic radiation from gigahertz to terahertz. This material here will change its transition point. So we build the same oscillator now, in which we have two setups. One setup is one setup in which we are placing practically in a transmission line the resistance of the VO2 loaded with a transistor. So this is our oscillator, and we are choosing ourselves the level of electromagnetic power. And another setup was that we place the material under the antenna that was designed to concentrate a certain frequency only on this material. And this is a very nice result that I show to you, is that here you are practically changing the switching point according to the power that you apply here. Here is in the gigahertz range. So you are practically building the simplest, smallest, and cheapest uncooled millimeter wave detection based on the sensitivity of the threshold voltage to the incident wave on this device. And these are practically the responsive feature that are in this paper benchmark according to the literature. Now, my last point, because my time is up, so 2 minutes, is that now we are moving for fabrication of these vanadium oxide-based devices that were essentially done by sputtering and pulse layer deposition to a technique that will make it even more compatible with CMOS devices and structuring devices, which is ALD. So our goal in the next year, and here I'm showing you here a first unpublished result, in which the morphology and switching in ALD deposited VO2 that can go down to few nanometer depend very highly to the temperature that you choose. And we are very near to reach similar 3 order of magnitude. We are not yet there, but we are at 2 order of magnitude and something. And we can structure the films in different ways depending on the annealing temperature and by playing with the temperature of the substrate. So now I want just to show you what this can be achieved. This is a 20 nanometer VO2 film, so it's extremely thin. PLD is the best material we have now in the lab. ALD is the one that is coming close to it. And here I want to show you different type of devices we are building. Here we are building sensor in which practically this switching hysteresis is depending on the temperature, but these sensors are extremely sensitive to strain. So we can build strain sensor that should be calibrated. It's combined stress and temperature sensing. Second thing, we have structured this at nanometer scale, and the property remains at nanometer scale, right? These are nanowire vanadium oxide. Of course, because of the form factor, they are more resistive, and we need a bit more voltage. But here, the phenomena remains in this nanostructure type of structure. So this may be particularly designed for a strain sensor. And then last point, something very exciting, I believe, to show to you. We ask ourselves, all this material are polycrystalline. We are making measurement on a number of grains. What is the proper, because when we build it on silicon oxide, the material is polycrystalline, right? If you were building on sapphire, maybe you get it crystalline. But the question was, what is the property of a single grain? So what we try to do is to make a metallization and test with an IFM the switching of a single grain of VO2. So these are 2 grains of VO2 that we reasonably suppose they are crystalline, each of them. Both, they show transition, and what I want to show you, what we do, we come with an IFM probe, and with this IFM probe, we test practically the switching of this grain between this metal contact and the IFM probe. So this property is fundamental to the material, right? It's not coming for any interaction. There are effects of grain-to-grain interaction, grain boundary, but as crystalline state, the VO2 has this property, and this is what you get on the next grain, right? A smaller voltage, the grain is smaller, so then it explains why this is reduced hysteresis this is larger. So you can imagine in the future, maybe, if with aluminum, with ALD, you can create a system in which you control individual grain deposition, then you go and contact and you make arrays of oscillator of nanoscale that are working like a highly sensitive neuron. With that, I am at the end of my talk, and just 3 conclusions. First, edge AI application need more sustainable technology for deployment in larger scale. For this reason, energy efficiency, reduced data proliferation, and abundant non-toxic material and processes would be needed. Second thing, neuromorphic hardware, I see it in strong relation with this type of application. And among many others that were cited in this conference, ferroelectricity in doped-High dielectric, multi-gate 2D semiconductor devices, and phase change material stands a very promising candidate. And last, this could have an additional, even higher value if the effort is made in such a way, material to system, to permit the 3D integration of such hardware or advanced silicon CMOS chip. So my colleague Abu, I agree with you. We have to do it on silicon CMOS. Thank you very much.
Yeah, Adrian, thanks a lot for this really inspiring talk. I learned a lot about many new materials and combinations, so 2D combinations for ferroelectric properties. Absolutely fascinating. Talk is open for discussions, so please go ahead.
Thank you very much for your talk. I'm John at Max Planck Institute, and I also work on vanadium dioxide for neuromorphic computing. I wonder about your vanadium dioxide for millimeter wave sensor. How would you compare to the state-of-art material for such sensors?
Yes. So this reminds me a question from one of the reviewers when we had this paper. So this is the reason we have, I think we try in this paper to have a benchmark. Like I am answering very simply. When you use for the first time and you make an application with an emerging material, certainly you will not be able to compete and beat the existing technology in all the figures of merit. But if you look at the type of uncooled type of sensor that I am looking now for, the power meter, right? This is a system that, as I mentioned, is extremely simple as architecture and will be cheap and can be integrated in many scenarios as a power meter control, right? Not make it like, even today I agree you can make a highly precise portable power meter. But again, I believe with this type of device, we can have power meter integrated in different type of application. And it will be even more interesting if some other groups that are working on that can show, because we had not fully capability to measure beyond 110 gigahertz. We measure from gigahertz to 110 gigahertz. But we believe this device will be even more interesting in the terahertz range, right? So yes, we define a set of benchmarks, we compare responsivity, we compare integration capability, we compare complexity, and then my message is, depending on the application, I'm sure it will find at least interesting niche of application beyond what is the state of the art, which in overall, I think it's probably better than this device.
Thank you very much.
So further questions? Let me raise a question. Your ferroelectric 2D material stack, Is it already theoretically completely understood where the ferroelectricity is coming from?
Yes, I believe that ferroelectricity in Hafnia, in doped Hafnia, right? In general,
Yeah, I mean that's
has a
different.
very
Yes.
strong group in Germany, in Dresden,
Of
in
course,
NAMLab.
yeah.
There are the one that were the pioneers in the field. So understanding the fundamental of this probably needs more exploration, but we see very clearly that when we are using this doping with silicon, with zirconium, what we are doing is practically the atom substitution, practically, right? And then depending on the size of the atom, zirconium versus oxide, then, and when you do the annealing, you create all this material that are ferroelectric compared to the Hafnia that is all polycrystalline, right? So there are different types of model and explanation that taking into account what I say, plus some people even demonstrate that you can achieve that even without doping and maybe with strain only, right? So at atomic scale, I think probably I cannot answer you completely what would be the full explanation. Like, you know, in PZT you have a very clear explanation, right? Is the swing.
Oh. But excuse me, so perhaps I didn't completely understand it. I thought the 2D materials, not the oxide, the 2D materials show ferroelectricity.
No.
Okay,
So
then it was my
this is not the
misunderstanding.
case.
Sorry about this.
So the ferroelectricity, I think, is in this this high doped case,
okay,
and then I think there are models.
That's different. Okay, this
different.
is
So
to a certain
in
extent
fact,
understood.
the 2D material that we have, we are just using it in tunnel FET to have the right band alignment for tunneling, and then we try to use a material that you can grow practically wafer level. So now we start to pattern it instead of just transferring flakes.
Yeah.
But it remains the same semiconducting property with band gap of a 2D material.
Anyway, very nice results. So if there are no further questions, let's thank Adrian once again.
Thank you.